The remarkable advancement of China's high-speed railway stands as a testament to the wisdom and dedication of countless researchers and engineers. Today, the country's operational high-speed rail network amounts to 48,000 kilometers, the longest of its kind in the world. The network is renowned for its exceptional speed, stability, and smooth operation, all made possible through continuous technological innovation and superb engineering. A vivid illustration of this engineering excellence can be seen in the now famous demonstration, where a coin remains upright in a train, even at top speeds. Among the many brilliant minds behind these achievements, railway track engineer Li Qiuyi stands out as an exceptional representative, embodying the expertise and commitment that have propelled China's high-speed rail to global leadership. Since embarking on his career about 2 decades ago, Li Qiuyi has successively completed the track design for more than 10 high-speed rail lines, including the Zhengzhou-Xi'an and Zhengzhou-Suzhou routes. He has continuously refined design standards, elevating China's high-speed rail track design and construction to world-class levels.
What is the initial estimate for how much it moves, specifically for the largest entire slab?
Under the rail, the movement is relatively significant, potentially reaching 1 to 2 millimeters.
This is a conversation between Li Qiuyi and his colleague during an experiment. Li serves as the Deputy Chief Engineer of China Railway Siyuan Survey and Design Group, one of the top research companies in the field of railway technology. Every month he oversees a team conducting lots of tests on high-speed railway track structures. His career in this engineering field started in 2004, when he joined the Wuhan-based company after obtaining a doctorate in railway engineering. 1 year later, he encountered a key research initiative launched by the then Ministry of Railways, the design of an integrated bridge and seamless points system for high-speed passenger lines. This research project was aimed at addressing the challenge of integrating points into bridges during the construction of China's high-speed railways, which was in the early stages of development at the time. In sections where high-speed trains need to switch tracks on bridges, seamless steel rail points, also known as turnouts, need to be laid. These seamless points, which can span several tens to hundreds of meters in length, must remain deformation-free to prevent the risk of derailments. Ensuring safety and stability requires coordinated design between the seamless points and the bridge structures. Li Qiuyi embraced the challenge with determination and resilience.
At the time, the installation of seamless points on bridges was considered a formidable engineering challenge worldwide, and the complexity of this research initiative was particularly acute. It so happened that my specialized expertise was in seamless track and bridge integrated point systems. After assessing my foundational knowledge and experience, I felt confident in my ability to spearhead this project. I therefore stepped forward and volunteered to lead the research effort.
As bridges undergo thermal expansion and contraction, with the magnitude of displacement increasing proportionally to bridge length, the steel rails of points similarly experience thermal-induced dimensional changes. When a bridge shifts, the points on it are designed to expand and contract. Their movements must be perfectly aligned. If they are not, the components of the points can lock up and fail to operate. This, in turn, would impede track switching and potentially lead to derailment incidents. Thus, Li Qiuyi and his team were tasked with identifying an optimal balance for deformation compatibility, minimizing displacement of the railway points to ensure safe and uninterrupted train operations.
At that time, the pressure was immense as we worked on this project. There was no prior experience to rely on, Every variable had to be calculated bit by bit and then verified step by step in the lab. The workload was enormous. What's more, I had volunteered to lead this research. If we failed, I would have felt I'd let everyone down. So during that period, I was often working around the clock in the office and the lab, sometimes even skipping meals, totally consumed by the research.
As the research progressed, Li Qiuyi drove himself and his team to work tirelessly, conducting repeated experiments on the seamless points structure on bridges. After half a year of analyzing and testing the deformation patterns of both the bridge and the points, they finally developed a comprehensive solution to counteract structural displacement in bridge-mounted points.
当时我们这个方案提交了之后啊，就是得到了这个
After we submitted our proposal, it was well received by peer experts. Our solution stood out and was adopted by the railway authorities. My colleagues were thrilled. For me, it felt like a breakthrough victory. I was so excited that I couldn't even sleep at night. That's exactly how it felt.
Li Qiuyi was subsequently appointed as the design chief for the tracks of the roughly 520-kilometer Zhengzhou-Xi'an high-speed railway, which began construction in September 2005. Designed for a speed of 350 kilometers per hour, the railway was planned to utilize a twin-block ballastless track system.
The twin-block sleeper is a critical component of the twin-block ballastless track system. It consists of two concrete blocks connected by a steel reinforcement truss resembling a dumbbell in shape. During construction, the entire sleeper is embedded into the track bed through casting. This ensures a strong bond between the steel reinforcement and the track bed, preventing cracks and loosening between the sleeper and the track bed.
One thorny issue puzzled them: how to fit an additional mechanical arm into a space originally designed for only 5. In conventional practice, the point system compatible with twin-block ballastless tracks relies on 5 switching machines to execute track switching. Each of the machines is mounted on concrete protrusions on one side of the foundation bed in the points area. These function like 5 mechanical arms fixed on concrete bases, working sequentially through pushing and pulling actions to achieve transition of the points. But the point section adopted for the Zhengzhou-Xi'an high-speed railway featured a more complex structural design. It required 6 such arms to act simultaneously during the track transition process to ensure smooth and reliable switching.
The points used in the Zhengzhou-Xi'an line were imported from abroad. They were protected by intellectual property rights. We could only adapt our ballastless track bed to match their turnout design. Foreign experts believed the task would be extremely difficult, as we had no prior experience with ballastless track systems in points areas. But we were determined to prove that Chinese engineers could devise our own solutions. We explored various approaches and eventually designed 6 mounting platforms for the switching machines.
The ballastless track bed serves as the foundation for the points, and the 6 switching machines must be installed on concrete protrusions on one side of this bed. But the available space, originally designed to accommodate only 5 such machines, posed a significant challenge: how to fit an additional unit without compromising the functioning of the whole system. If the position of any switching machine or its supporting protrusion was improperly designed, it could hinder smooth point operation and jeopardize train safety. Li Qiuyi and his team conducted extensive simulation studies and pioneered an innovative ballastless trackbed structure for the switching machines in the point zone. They reconfigured the original design by replacing the 5 separate concrete protrusions with a single elongated protruding plate, effectively converting isolated points into a continuous surface and expanding the installation space. This allowed the 6 switching machines to be arranged in a 4+2 configuration, 4 in the front and 2 in the rear, thus ensuring synchronized operation and reliable switching performance. But a new issue emerged after resolving the layout challenge of the switching machines.
During the design of the switching machine mounting platform, we encountered a problem of insufficient anchorage strength in the anchor bolts. Calculations showed that each bolt needed to withstand a vertical force of 6 tons and a lateral force of 7 tons. This load is equivalent to the weight of 2 or 3 passenger cars acting on a single bolt. Since the bolt alone couldn't handle such forces, we introduced a special design, adding small lateral wings, essentially curved hooks, to the assembly. These hooks significantly improved the bonding between the bolt and the concrete, enabling the system to achieve the required load-bearing capacity.
Leveraging the positional relationship of the bolts, Li Qiuyi designed a steel plate with 2 bolts welded at each end to serve as the foundation for mounting the switching machines. To further reinforce the structure against the potentially insufficient vertical load capacity of the protruding plate, he also welded 2 hooks of 5 centimeters in diameter beneath the steel plate to fasten the switching machine platform. This solution effectively addressed the fixation strength issue of the switching machines, ensuring the safe operation of the points on the Zhengzhou-Xi'an high-speed railway. However, after overcoming that challenge, another problem arose. To enable high-speed trains to run smoothly and swiftly, continuous welded rail, also known as seamless rails, had to be used. But back in 2005, there was no existing data to determine the type and specification of the fasteners required to fix the rails. So, what approach did Li Qiuyi adopt? In traditional jointed tracks, a gap exists every 25 meters. When trains pass over these gaps, significant impact forces are generated, accompanied by metallic collision noises. At high speeds, these impacts become even more intense, leading to accelerated wear and potential damage to both rails and train wheels. Therefore, to ensure the safe and stable operation of high-speed trains, the rails had to be welded into a seamless continuous length. They are then firmly anchored to the track foundation using sets of high-strength fasteners. Li Qiuyi led his team conducting tests and verification on the lengthwise resistance of fasteners used in high-speed railways.
At the time, we lacked specific resistance parameters for these fasteners, which caused uncertainty over the entire design of the continuous welded rail. We had no clear idea whether the design was safe, and doubts remained. To obtain accurate real-world parameters, we carried out on-site experiments to simulate the actual resistance behavior of the fasteners under train operation.
The natural phenomenon of thermal expansion and contraction is a major threat to the integrity of continuous welded rails. In traditional jointed tracks, gaps spaced every 25 meters allow the release of stress caused by thermal expansion and contraction. In contrast, the stress generated in continuous welded rails due to temperature changes has nowhere to go, transferring the tension entirely to the fasteners.
The function of railway fasteners is to clamp the rail firmly while resisting displacement caused by thermal deformation. As temperature fluctuates, the rail expands or contracts. In extreme cold, this can lead to rail breakage, while in high temperatures, the rail could bend or warp sideways. Both scenarios can result in derailment accidents. Given China's vast territory, temperature variations differ significantly across regions. Designing continuous welded rails requires collecting meteorological data from various locations. Our team gathered rail temperature data from 254 cities to determine the design parameters for the lowest and highest rail temperatures. These parameters were then used to simulate the thermal stress within the continuous welded rail system, forming a critical foundation for our design.
At an engineering lab of China Railway Yuan Survey and Design Group, there was a test bench where Li Qiuyi and his colleagues secured a section of rail using fasteners. They placed a jack against one end of the rail to simulate the force exerted on the fasteners due to thermal expansion and contraction. It was through hundreds, even thousands of such tests that the team gradually increased the jack's thrust on one end of the continuous welded rail. When the force reached 15 kilonewtons, the fastened rail began to warp. Li Qiuyi concluded that the maximum load the fasteners could withstand was 15 kilonewtons. Therefore, as long as the force on the fasteners remained below that number, the continuous welded rail would be firmly held in place without deformation. Amid this intense period of work, Li Qiuyi faced numerous professional challenges. Yet a shared habit between him and his wife played an unexpected role in helping him navigate these difficulties more efficiently. His wife, Li Qiuyi, vividly recalled how they helped each other during that period.
Our child was still young back then and usually went to bed around 10 p.m. After that, my husband and I would take out our notebooks and go through the items one by one, discussing each in detail. Whenever there was something I didn't understand, I would ask him for advice. That's how it was. After our child fell asleep, we would continue with our work.
Around the same time Li Qiuyi embarked on his career in 2004, his wife was also hired as a track engineer at the same company. To quickly adapt to their roles, the couple encouraged and learned from each other.
That period was truly a journey of discovery together. She raised questions, and I had to think about how to answer them. In a way, she pushed me to grow, because in order to explain things clearly, I had to reflect deeply on those issues myself. It was indeed a demanding time for her, and she studied very hard. But learning together and encouraging each other also made it a rather joyful process.
Whenever a new solution was proposed through their discussions, Li Qiuyi would return to the laboratory to conduct simulation tests on the seamless track system. After several months of effort, he obtained some key data. The low-resistance fasteners could withstand a force of 4.8 kilonewtons. This result met the structural requirements for rails on bridges and provided critical data for the compilation of China's national design specifications for continuous welded rail systems.
应该是规范的制定就是标志着无缝线路取得了这个重大的技术进步。
It can be said that the establishment of these specifications marked a major technological advancement in continuous welded rails engineering. The standards have played a vital role in guiding the design and construction of continuous welded rails in China. Through years of hard work, our team endured many challenges and setbacks, and ultimately we succeeded.
In February 2010, after more than 4 years of construction and the dedicated efforts of countless engineers and technicians like Li Qiuyi, the Zhengzhou-Xi'an high-speed railway was officially opened. For Li, the project held both professional and personal significance.
看到我们辛苦的努力得到了这个回报以后我们都是非常高兴的。
We were all immensely pleased to see our hard work pay off. The Zhengzhou-Xi'an line demonstrated that our designs and solutions effectively addressed the challenges during its construction. At the same time, it provided valuable experience for the future development of high-speed rail track design and engineering in China.
Li Qiuyi's commitment to improving rail travel stems from first-hand experience. Growing up in northeast China, his first long trip was to Hunan province in central China for college. At that time, the train journey between his hometown and his campus required a transfer in Beijing and took over 2 days in total, giving him a deep first-hand understanding of the inconveniences of long-distance travel. This experience planted a seed in his heart, a determination to change this reality. After completing his undergraduate studies at Changsha Railway College in 1995, he pursued further education and dedicated himself to research in high-speed rail track design. Through the refinement of one project after another, Li Qiuyi has grown from a junior engineer to deputy chief engineer of China Railway Siyuan Survey and Design Group. At the 2017 National Science and Technology Progress Award ceremony, Li Qiuyi received the first prize for his participation in the design and engineering of continuous welded rail used in complex environments. His research successfully resolved the global challenge of seamless turnout technology on high-speed railway bridges, marking a new height in China's railway track engineering. In recognition of his achievements in his field, Li Qiuyi was awarded the National May 1st Labour Medal in 2023. The medal is awarded to individuals and groups who made outstanding contributions to China's economic and social development. Humble and diligent, Li Qiuyi is now aiming for new heights.
Although we have accomplished many tasks and completed numerous design projects, we still face many new challenges. For instance, China's high-speed railway is currently developing and testing technologies for 400 km/h operations, and our track technology must keep pace with this progress. Moreover, we aim to integrate artificial intelligence and big data with our track technology to achieve intelligent design, construction, and maintenance of rail systems. This represents a new direction for our future development.
Today, the high-speed rail journey from Li Qiuyi's workplace in the central Chinese city of Wuhan to his hometown in northeast China takes just 12 hours, a significant progress compared with the more than 2-day-long journey he had to make when he was a college student. What makes him especially proud is that the line he takes is the one he once poured his heart and effort into designing.
As railway builders, we sincerely hope that the high-speed rail networks we construct can extend in all directions, achieving interconnectivity and making travel more convenient for the people. We will continue striving towards smarter, more efficient, and greener technologies to further improve China's rail transit infrastructure.
With that, we conclude this edition of Footprints. Thanks for listening. I'm Bob Jones. If you're interested in hearing more about the lives of ordinary but incredible people in China, follow us on your favorite podcast platforms. Just key in Footprints and you can find more stories anytime, anywhere. We'll see you next time. Bye for now.